Hey guys, and welcome to another video in my series of videos on statistical physics and thermodynamics. In the last video we went through the equipartition theorem and derived it formally, and basically saw how it could be applied to both a monatomic ideal gas and a diatomic ideal gas as well. So remember those two extra degrees of freedom meant that some of the properties and the statistics of the energy stuff increased from 3 to 5, and so that was a direct result of the fact that every quadratic term in the Hamiltonian contributes kBt over 2 of energy. So that was all in the last video. In this video we're going to be sort of taking a little detour, but we're still going to be kind of applying the equipartition theorem. And we're going to be looking at what's called the Einstein model. And the Einstein model is basically a model for determining how the heat capacity varies according to temperature within a solid. So let's say we've got like a solid right here. And the solid obviously has a certain heat capacity. That's the property of the solid. And it's an environment with temperature T. And so the question is, how does the heat capacity vary with temperature? Well, let's use the equipartition theorem and the first law of thermodynamics to derive this. So what is the heat capacity then? Well, CV, the heat capacity at constant volume, remember we're talking at constant volume since it's a solid and the solid's not likely to change its volume, is equal to the derivative of the internal energy with respect to temperature, keeping the volume constant, of course. So what's the internal energy? Well, from the equipartition theorem, we said that the internal energy is equal to 1/2 kBt multiplied by the number of degrees of freedom. And how many degrees of freedom did we say there were? Well, let's go ahead and analyze this solid a little more carefully. So we've basically got the atoms in the solid, which are of course free to move around, but the way in which we think of them, we tend to think of them as if they're all kind of joined by springs, like all the bonds between the atoms are all kind of springs, if you like. And so springs, what does that mean? Well, that means that they're a harmonic oscillator. Of course, if you remember simple harmonic motion, then you'll remember that say you have like a mass here and a spring here, and the potential energy of the spring is of course 1/2 multiplied by the spring constant multiplied by the displacement squared, and that's kind of like the potential energy of a spring. And you can kind of treat this as like a sort of a harmonic coupling, if you like, between the atoms, and so that is a very useful model for this. So we need to just identify this term right here. We need to identify how many degrees of freedom there are in this Einstein solid. Well, let's just go ahead and put some more numbers to it. We've got n particles in the solid, and each one of those particles is going to be able to have movement in each of the 3 different directions. So it's going to be able to move up and down, it's going to be able to move sort of this way right here, back and forth, and it's going to be able to move left and right. And so these are of course the 3 Cartesian coordinates. So there's 3 degrees of freedom right there. But there are also extra terms in the Hamiltonian. There are extra degrees of freedom. If you remember what the Hamiltonian for a harmonic oscillator is, well, it's the sum of the kinetic energy plus the potential energy V. And so we've got this P squared over 2m, which is what we said the kinetic energy was in the last video. And we've also got the potential energy, which I just said was 1/2 kx squared. So this is our Hamiltonian, 1/2 kx squared. And of course, you're going to have one of these in every dimension. So you're going to have 3 momentum coordinates and you're going to have 3 position coordinates. And so therefore, what are you going to end up with? Well, you're going to end up with a total of 6 degrees of freedom. So there are 6 degrees of freedom in this model, and it's just like what we derived in the last video. When we were deriving the equipartition theorem, we said that there was 3 momentum coordinates and 3 position coordinates, and so that gives us a total of 6 degrees of freedom. So what is this term right here going to be? Well, there's 6 degrees of freedom for each particle, but of course there's n particles, and so therefore this term is just going to be 6n, and this is going to reduce down to 3n kBt. And it really couldn't be simpler to be able to differentiate this with respect to temperature. So we can see that the heat capacity is equal to the derivative of this with respect to temperature. Well, that's not too hard, is it? It's just going to be 3n kb. 3 times the number of particles multiplied by the Boltzmann constant. And if you remember what this term is right here, that is just simply 3r. And 3r is just it's just a number. It's just a complete constant. It doesn't depend on anything. Or 3nr, I should say, multiplied by the number of moles. But if you define the molar heat capacity, little cv, which is equal to big CV divided by n, then it's just simply 3r, or 24.9, or thereabouts. So it's just a complete number. And so, therefore, the heat capacity of any solid per mole should be exactly the same, and it should be the same across all temperatures. And this right here, this CV equals 3 nkb, or 3nr, this is what's known as the Dulong-Petit law. And it basically just says that the heat capacity is a constant and it doesn't vary with temperature. However, I hate to burst your bubble, but this law does not hold for all temperatures. Unfortunately, physics is not that kind, and it's not true that all solids have exactly the same heat capacity for all temperatures. It would be nice, but unfortunately it isn't, and so we're going to have to go into some deeper models into how we can determine the heat capacity. So how does it actually change, first of all? So let's go and see what's actually happening. So let's go ahead and graph the heat capacity on the y-axis versus temperature on the x-axis. So what's this graph going to look like? Well, for low temperatures, we find that the heat capacity is much lower than you'd expect, but it rises very quickly at low temperatures. But at high temperatures, it flattens off, it plateaus, if you like, and the point in which it plateaus, rather unsurprisingly, I suppose, is this. It's this 24.9. Remember, this is the molar heat capacity. I'll just put CV divided by n just so that we know what we're talking about. This is 24.9 joules per mole per Kelvin. And so the heat capacity of any solid approaches this, but it never sort of really gets there. And so obviously we're kind of half right with this derivation, and this, and it works for high temperatures, this model, but it's not really explaining what's going on down here. Of course, the heat capacity, according to this model, shouldn't vary with temperature. So why is it varying with temperature? What haven't we considered? So that's what we're going to be talking about today. The first model we're going to be talking about is what's called the Einstein model. So let's get right into the Einstein model. So Einstein considered the solid in much the same way that we just considered it then. So it's a kind of a block, a lattice cube right here, a cubic lattice full of springs attached. So it's basically lots of atoms, all of which are attached by these kind of metaphorical springs right here. They don't really exist. I didn't draw that very well, did I? And each one has a certain amount of kinetic and potential energy, as before. But you may know from quantum mechanics that the energy of a harmonic oscillator is what's called quantized. in certain units. And so this is kind of the first step really to being able to get anywhere, is to assume that the energy levels are in fact quantized. And you'll probably know that the formula governing what the quantization is equal to, is the energy is equal to h bar omega. So it's quantized in units of h bar omega. And so the nth energy level would therefore just be n h bar omega. In fact, that's nearly true, except we need to account for what's called the 0 point energy. This is what's called vacuum fluctuations in energy. And the 0 point energy is 1/2 h bar omega. So we actually have to add this 1/2 in right here. This is all fairly well established in quantum mechanics, and it's called the 0 point energy. So in fact, you actually get that the energy values are 1/2 h bar omega, 3/2 h bar omega, 5/2 h bar omega. So they go up in half integers rather than in full integers right there. So that is what the formula for what's called the eigenvalues of the harmonic of the quantum oscillator are. And this is what we're going to be using in the Einstein model right here. Remember, h bar is simply 1.055 times 10 to the minus 34 joule seconds, and omega right here is of course the angular frequency. Remember, omega is 2 pi multiplied by the actual frequency, but the reason why we use omega is because of course h bar is h/2 pi, and omega is of course 2 pi f, so this is actually exactly the same as E equals hf, but except we've defined it as h bar, except we've used h bar omega. The reason why we use h bar omega is just because it's easier to take the sign of, pretty much. It's easier to do trigonometric operations on, pretty much, but that's the only reason. So we know our energy eigenvalues, and so what are we going to do? Well, we're actually going to calculate the partition function for this solid, for the Einstein solid. And if you remember from before, if we know the partition function, then we actually know everything. And the partition function we can simply calculate by adding all of the energies up. It's a weighted sum of all the exponentials of all the energies. And so we can calculate what the partition function is, and from that we can derive the internal energy and hence the heat capacity. So let's go ahead and do that. So I want to start off by deriving the partition function for just one particle. So we want the one particle partition function, and this is of course equal to the sum ranging from j equals 0 to infinity. Remember, this right here doesn't have any sort of upper limit, so it could technically go on forever. You could technically have infinite energy. At least we're going to assume that for this calculation. And it's a weighted sum of all of the exponentials weighted by the temperature. So e to the minus beta ej is what is being summed over. So what is our ej's? Well, I've used n here, but in this case j is our summation index, so I'll just rewrite this as j. ej is j plus 1/2 h bar omega. So all I've done is just change the dummy index from n to j. I haven't done anything at all. N and j don't really mean anything, they're just integers which are being summed over. So let's go ahead and substitute this right here into our exponentials. So we have the sum from j equals 0 to infinity of e to the minus beta. Instead of ej, we're going to write j plus 1/2 h bar omega right here. So all we've done is just substituted that into this expression here. And so what can we do with this? Well, you'll notice we'll actually get two different terms right here. So we'll because of course we've got this plus here, we will actually get two different terms inside this exponential. So you'll get an e to the a plus b, something of that form. And what do we know about our laws of indices? Well, we can simply separate that to be e to the a multiplied by e to the b. So let's just go ahead and write this out again, just so we know what we're doing. So we've got the sum from j equals 0 to infinity of e to the minus beta h bar omega j minus, remember we've got a minus sign right here, beta h bar omega divided by 2 right here. So we just have, so I've just expanded this bracket out, and as you can see, we can now just separate this into two separate exponentials. So that can just come over here. So this is all, that's all in brackets, and that's all in brackets right there, just so we know what we're doing. Now you'll notice that this term right here does not have anything to do with j in it, so it's not actually being summed over, and hence it's more convenient to just pull it outside the front, so we don't really have to worry about it. So we've got e to the beta h bar omega divided by 2 multiplied by the sum from j equals 0 to infinity of e to the minus beta h bar omega j. Alright, looking good so far. So what are we going to do now? Well, I'm actually going to do a very subtle thing now. I'm actually going to rewrite this in a different form, and you'll see why I've done this in a moment. So let's just rewrite this. So e to the minus beta h bar omega over 2. Leaving that as it is right there. And then we're going to have this big sum of e to the minus beta h bar omega. And what I'm going to do is I'm actually going to put a little bracket in front of this, and it's all raised to the power of j. Now, of course, you're probably going to say, this is exactly the same. I kind of knew that. Why would you write it like that? Well, it's just easier to see what I've done in the next step. So this is why I've done it. So what am I going to do? Well, I'm actually going to use a mathematical approximation right here. And this is a very well-established mathematical sum identity. And it is, I'll just do it in a different color just so we can see what we're doing. It is that the sum of any number ranging from n equals 1 to infinity, the sum of any number raised to the power of n is equal to 1 over 1 minus that number right here. This is a mathematical identity. I'm not going to derive it. It's very well established, and we're going to be using it to get rid of this sum term right here. So what are we going to do? How are we going to use it? Well, we can identify that this x term right here is just the term in brackets right here. So you can see why I've put this in brackets right here, because of course j is of course the dummy summation term, and this x right here is just whatever's in the brackets right here. So we can simply just match it up with this right here. Since this x can simply just be replaced with this, we can write that the partition function is equal to, remember we had this factor out the front, e to the minus beta h bar omega over 2. And instead of this sum, we're now going to simply replace it with 1 over 1 minus e to the minus beta h bar omega. So that's nice. So that's kind of got rid of our sum right here. And let's just go ahead and tidy this up. Let's put the e on top of the fraction. E to the minus beta h bar omega over 2 divided by 1 minus e to the minus beta h bar omega. And I'm now going to just do a little adjustment. I'm just going to multiply both sides of this fraction by exactly the same thing. We're going to multiply it by e to the beta h bar omega over 2. So I'll just write that. I'm going to multiply both sides of the fraction by e to the beta h bar omega over 2. So what's that going to do? Well, that's just going to make all of these terms multiply all these terms by this factor right here. So e to the minus beta h bar omega over 2 times this is just going to be, well, just going to be 1, isn't it? Because they're just going to cancel out. And this term is going to become e to the beta h bar omega over 2. And this term right here is just going to become e to the minus beta h bar omega over 2. So it's e to the minus beta h bar omega. We're adding a same thing over 2. So it's just going to become minus that over 2. And there we go. This is our partition function. Now, if you know your hyperbolic trigonometric identities, which I must say I don't, I've completely forgotten them. We learnt about them in first year, and since then I've completely forgotten them. But if you look them up on Wikipedia, then you'll see that this is actually equal to 1/2 of the cosec, half of the cosec of beta h bar omega over 2. This right here is actually the definition of the cosec function. If you happen to remember that, then well done to you. But this is actually the cosec of this term right here. And it's actually going to be easier to leave it in terms of this hyperbolic identity, simply because I'm just going to sort of cheat and use identities for when I'm doing the differentiation, because of course we're going to have to differentiate this z in order to get the internal energy. So z is actually 1/2 of the cosec of this term right here. Now, I'm just going to make another substitution right here. I'm just going to introduce a new term. And this term is what's called the Einstein temperature, theta E, right here. And I'm defining it to be h bar omega divided by kb right here. So this is what I'm calling the Einstein temperature. Why have I called it the Einstein temperature? Well, you'll notice that this actually has units of temperature. So h bar omega is, of course, the units of energy, and you divide a unit of energy by the Boltzmann constant, you're going to get something with the units of temperature. And so this Einstein temperature is actually a direct function of the frequency. And so the Einstein temperature basically just measures what the frequency is of the harmonic oscillator. So why are we calling it a temperature? Well, it has the same dimensions as temperature, but interesting things happen when T becomes the Einstein temperature. So really, when we're talking about heat capacity, we're talking about what happens when T is much less than the Einstein temperature, and what happens when it's much greater than the Einstein temperature. So it's useful to have this kind of quantity we've just defined, so we can have something to sort of compare it to, compare and contrast, if you like. So there we go. This is the partition function for one particle. So what's the internal energy per particle? Well, the internal energy is, of course, minus the derivative, remember our magic box relation right here, the derivative with respect to beta of the log of the partition function. So this is U1, it's the internal energy per particle. So let's go ahead and just substitute this in. So what are we going to get? Well, we're going to get minus the derivative with respect to beta of the logarithm of 1/2 cosec of beta h bar omega divided by 2. Alright, there we go. And if we use our log laws, then we'll find that this is equal to the derivative with respect to beta. We're going to have a big bracket because we're going to get two terms. Ln of 1/2 plus ln of cosec of beta h bar omega over 2. So there we go. This is what we've got to do. We've got to differentiate this with respect to beta. And I hope you guys can immediately see that this is just going to not contribute anything at all. Ln of 1/2 is not a function of beta, so it's just gonna completely disappear. So now we just got to differentiate this, and you guys probably won't know the derivative of cosec. I wouldn't expect you to know that. But the derivative of cosec of x, so d by dx of cosec x, is simply equal to minus cof x multiplied by cosec x. Now you guys almost certainly will not know this, and no lecturer in the world should expect you to know that. They will give that to you in the question most likely, or you can just easily look it up on Wikipedia or something like that. So how are we going to differentiate this function right here with respect to beta? Well, since we've got a log function, then we're going to have 1 over whatever's in the log. So we're going to have simply cosec of beta h bar omega over 2. This is going to be in the denominator right here. And on the numerator, we're going to have the derivative of cosec of beta h bar omega over 2. So what did I say that was? Well, the derivative of cosec x is minus cof x cosec x. So remember, we're going to get a minus right here. Don't forget that minus sign. So it's going to be minus from this minus over here, cof of beta h bar omega over 2 multiplied by cosec of beta h bar omega over 2. So this is our internal energy, except we just need to add on the derivative. Since we've kind of used the chain rule, we're differentiating with respect to beta, not with respect to beta h bar omega over 2. So we just need to multiply this by h bar omega over 2, which is of course the derivative of this function with respect to beta. So yeah, that's kind of a complicated differentiation process. I can definitely appreciate that. But basically what I've done is I've used the differentiation with respect to x of log x, which is equal to 1 over x. The derivative with respect to x of cosec x, which you're not expected to know, and just simply differentiated this function with respect to beta. So there we go. That's kind of the hard bit done, if you like. And you can immediately see that these cosec terms are just going to cancel. The minus terms are going to cancel. So the energy per particle is just simply equal to h bar omega over 2 multiplied by cof of beta h bar omega over 2. So there we go. There is our energy per particle. Equally, you could write this as exponentials. Cof consists of many exponentials. But since we've got to differentiate this again, then it's much easier to leave it in terms of hyperbolic functions. So that's the energy for one particle. But of course, we have a total of n particles. We have a total of n particles in 3D. But we've got to be careful, because remember, we've only really considered one dimension. So this so far has been a one-dimensional model. And so, therefore, we have to multiply this n by 3. So it's actually exactly the same thing as saying 3n particles in 1D. Now, I know that's a little bit of a weird step right here, but it's far easier if you just do it this way than having to do it the long way around with working out the different coordinates of the Hamiltonians. I hope you guys can see why it's 3n particles in 1D. Basically, adding extra dimensions basically increases the number of degrees of freedom, and from the equipartition theorem, then obviously you're going to get 3 times as much energy from that. So there are 3n particles in 1D. So what is the total energy, the internal energy for all the particles? Well, we're just going to simply multiply this term by 3n. So we're just going to get 3n h bar omega over 2 times cof of beta h bar omega over 2. And of course you could write this in terms of the Einstein temperature as well. So that's 3 over 2 n h bar omega, and you're going to get cof of the Einstein temperature divided by 2t, simply using the definition of the Einstein temperature. So we've got the internal energy for all of the particles, which is brilliant. I know that was a little bit of a weird step. I can definitely appreciate that. But basically, yeah, you're multiplying it by 3n simply because you have 3n particles in one dimension. That's how we're kind of modeling it. So finally, we're pretty much ready to do the heat capacity now. So all we have to do is differentiate this with respect to temperature, and we are laughing pretty much. What would actually be useful is to use this form right here of the internal energy, because of course the heat capacity, if you remember, is du by dt. So it's better to have the internal energy as a function of temperature rather than having it as a function of beta. The reason why we used beta before is because of the magic box relations made it easier. The magic box relations use beta, but the heat capacity is just easier to use this form right here. So the derivative of u with respect to t, let's go ahead and do it. So it's d by dt of 3 over 2 n h bar omega cof of theta e divided by 2t. Remember, the Einstein temperature is not a function of temperature, it's just a quantity which has dimensions of temperature, which is actually a function of frequency. So let's go ahead and do this. A lot of this stuff is just simply going to come out the front. So we're just going to get 3 over 2 n h bar omega multiplied by the derivative with respect to t of cof of theta e over 2t. And now you're going to want me to tell you what the derivative of cof is. I'll be quite amazed if you did know what it was. I certainly don't know. I don't think I know what it is right now if it wasn't on my little sheet of paper that I'm looking from. So the derivative of cof of x, so d by dx of cof x is equal to minus 1 over sine squared. I can't even spell shine. Sine hyperbolic squared of x right here. So there we go. That's what we're going to be using. The derivative with respect to x of cof x is equal to minus 1 over sine squared x. And so we can now just use the chain rule, much like how we did before, to write what the heat capacity is. And so d by dt of cof, so that's going to be minus 1 over sine squared x. So we're going to get minus 1 over sine squared of theta e divided by 2t right here. But we have to remember to multiply it by the derivative of whatever is in the bracket right here. So what is the derivative of this with respect to temperature? Well, we've got a constant, essentially. This term is a constant, multiplied by 1 over temperature. So we're going to get this constant, theta e over 2t. And we're also going to get a minus 1 over t squared right here. So again, I've just used the chain rule. I've used the fact that the derivative with respect to x of 1 over x is equal to minus 1 over x squared right here. So that's the thing that I've used. You can immediately see these minus signs are going to cancel. Now, if you remember, h bar omega is actually related to the Einstein temperature. Remember, the Einstein temperature is simply a function of frequency. And so if we remember that the Einstein temperature is equal to h bar omega over kb, then h bar omega is, of course, the Einstein temperature multiplied by kb. So we can now substitute out this for the Einstein temperature right here. So 3 over 2n. Instead of h bar omega, we're going to write theta e multiplied by kb. All right. We've got another theta e here, so this is going to become theta e squared divided by 2t, There shouldn't actually be a t there. I do apologise. I'll have put a caption or something. So we've got that. We're going to divide it by another 2. There's another 2 right here. A 1 over t squared, and we've got this whole sine term, 1 over sine squared theta e over 2t. So let's go ahead and just tidy this up a little bit. We're going to get 3 over 4 n kb theta e squared, 1 over sine squared theta e over 2t right here. So there we go. Here is our heat capacity relation right here. And as you can see, the temperature dependence of it is very weird. It's got a rather odd temperature dependence. It's a minus 1 over t squared to begin with, but then of course you've got this sine term right here. So yeah, it's a very odd temperature dependence. And so what can we do? Well, what we like to do sometimes in physics is sort of see what happens when certain terms are much larger than other terms. And in particular, we're going to see what happens when the temperature gets large, right? So what happens when the temperature gets large? Well, this term right here is going to get very small because as you can see, it's a 1 over temperature term, and so this term in the bracket is just simply going to get very small. So what happens when we take sine of a very small number? Well, similar to sine, if you remember the famous approximation that sine x is roughly equal to x for small x, this is also true of sine as well, which is quite nice, quite convenient that. So sine x is also approximately equal to x at low x right here. So if whatever is in this bracket is low, then you can simply substitute it for the term itself. So what are we going to get? Well, of course we've got a sine squared term, so this term is actually going to get squared right here. So let's go ahead and write the heat capacity, 3 over 4 nkb theta e squared over t squared, and we're going to get 1 over this term squared right here using the approximation. So we're going to 1 over theta e squared divided by 4t squared. And just tidying that up, that's going to be 3 over 4 nkb theta e squared over t squared times 4t squared divided by theta e squared. And I hope you guys can see by now that a lot of stuff is going to cancel. Firstly, we can cancel the temperature squareds, we can cancel the Einstein temperatures, we can cancel the 4s if I'd have just written the 4 correctly. So what are we left with? Well, barely anything. But we are in fact left with 3 nkb as the heat capacity. And what is this? Well, this is the Dulong-Petit heat capacity, of course, that we just derived earlier. The Dulong-Petit law. So we've recovered it. Brilliant. That's really cool. So the Einstein model brilliantly predicts that at high temperatures, remember, this approximation was only valid for high temperatures because this is what allowed this term to get so low, which enabled us to use the approximation. At high temperatures, the heat capacity approaches this right here, 3 nkb, which is exactly what the graph said. The graph said that at very high temperatures right here, then this right here is of course 3 nkb, which is what the Dulong-Petit law originally proposed. So the Einstein model works very well with high temperatures. So that's brilliant. What about at low temperatures? Well, let's go ahead and do a similar thing. Let's go ahead and write out what the heat capacity originally is. So it's 3n theta e squared kb divided by 4t squared. This is the result we got for the heat capacity, multiplied by 1 over sine squared of theta e divided by 2t. So this is our heat capacity general expression. So what I'm actually going to do is I'm actually going to write shine in terms of exponentials, because remember shine is just simply a combination of exponentials. I'll write out what shine x is. Shine x is simply equal to 1/2 of e to the x minus e to the minus x right here. So if we want 1 over shine, then we're going to simply have exponentials in the denominator with a little 2, I think, in the numerator. So let's go ahead and just rewrite this. I haven't done any approximations yet. We're going to get all that, and instead of shine, I'm going to simply write 2 over e to the theta e over 2t minus e to the minus theta e over 2t. So there we go. This is just 1 over shine, and remember, of course, it's squared, and the 2 should be squared as well, which will give us a 4 right there. And immediately see the 4s are going to cancel rather nicely. And so what happens when the temperature is small? This is what we're talking about. Well, if we have a look at this term right here, this term doesn't actually matter. This term is what's going to give us the sort of the extremes, the extremities. So if the temperature is small, well, this term right here in the exponential will become really massive. It will become really, really big, because this is going to become an incredibly large number, because of course the temperature is really, really small. So this term will become massive. But what about this term? Well, we've got an e to the minus, and if we have a look at our graph of e to the minus x, if we have e to the minus an incredibly negative number, and if we have e to the minus an incredibly small number, then it's just going to become negligible. So this term right here is going to become negligible compared with this term right here. So what we can actually do is just drop this term right here, because it's not contributing anything at all. And so we get that the heat capacity is 3n theta e squared kb divided by t squared. And remember, we had 1 over this squared, so it's going to be e to the minus theta e divided by t, because remember it's squared, so that will eliminate that half right there. So here we go. There is our formula for the Einstein prediction of the heat capacity at low temperatures. And if I simply make a substitution, if I let x equal h bar omega over kBt now, or equivalently the Einstein temperature divided by the temperature, so x is just some dimensionless quantity, then this simply becomes 3n x squared kb divided by t squared times e to the minus x. And so what does this look like when graphed? Well, it's an x squared e to the minus x, so it means it's going to start off by looking like an x squared graph, which is good. It's going to start off looking like an x squared graph, but of course the e to the minus x means that it's going to sort of modulate. And this is good. However, it does not agree with experimental results, unfortunately. It might look like it's the same, but unfortunately it doesn't actually agree with experimental observations of the heat capacity at low temperatures. In fact, the experiment shows that the heat capacity at low temperatures is proportional to the cube of the temperature. So it shouldn't really have any of these exponentials in right here. It should simply be proportional to the temperature cubed. And this is very well established experimentally. A lot of metals behave like this. At low temperatures, their heat capacity is dependent on the cube of the temperature. So the Einstein model in fact fails for low temperatures. So even though it's very good up here, it gets the it gets the Dulong-Petit limit of 24.9 joules. It is not very good down here. It actually sort of under predicts what you're going to get. You might think it's very similar, but it's actually the incorrect prediction. So we're not quite there, but this is resolved in what's called the Debye model of heat capacity. Now, the Debye model is a very different approach to heat capacity. So rather than calculating the partition function and then from which calculating the internal energy, we actually have to introduce this idea of what's called a phonon. And this will be covered not for a little while yet. It will be covered in my series of videos that I'm planning to do on condensed matter physics. And this will be a few videos in, but the Debye model uses phonons, and basically what a phonon is sort of movement of the lattice itself. So the lattice positions are moving, and that's sort of what generates the temperature. But we'll get into that when we come to talk about condensed matter physics. But the Debye model does correctly get that CV is proportional to T cubed. So the Debye model was a success. The Debye model does correctly get the heat capacity at low predictions, and it gets it mathematically, and yeah, I'll be deriving it in a few videos time. But that's a summary of the Einstein model. I hope all that made a good deal of sense. I know I used a lot of substitutions and a lot of maths in this video, but really all the maths is neither here or there really. It's the physics that matters. The physics of how the heat capacity changes with solids. That's the important bit. Just remember this graph pretty much. This graph is very, very useful. At low temperatures, the heat capacity varies with proportion to the cube of the temperature, and at high temperatures it simply tails off and plateaus at the Dulong-Petit limit. So there we go. That is the Einstein model, and I'll see you guys in the next video.